Introduction to Lewis dot structures. Lewis dot structures. They are a method to represent the valence level electrons in an element that only have valence level electrons in the s and p orbitals. So it really only works for the lighter elements, and we'll see this in the next slide. So here on the periodic table, you can see the s elements that it works for and the p elements that it works for. So it's really only the first three rows of the periodic table that the Lewis dot structures will work for. Valence level electrons are the outermost electrons. They are the electrons in an atom past the last noble gas. So if you want to write an electron configuration for an element in the noble gas core, it's the electrons that are written. And I'll show you an example in 1 second. So for magnesium, the electron configuration using the noble gas core notation is the neon is our noble gas, and then past that it's 2s2. So magnesium has 2 valence level electrons. And there's actually an easier way to figure this out. For each group number, it also equals the number of valence level electrons. So you can see on here I have the group numbers, and the groups go up and down, of course, numbered on here, and the group number equals the valence level electrons. So group 1 has 1, group 2 has 2, and so on and so forth. So here's an example for single elements. Nitrogen Lewis dot structure. Nitrogen's group 5, so there are 5 valence level electrons. And all you really need to know is the electrons don't pair up until they have to, and that's Hund rules, and it's the same as when you wrote out electron configurations. And here's some elements, the lighter elements that the Lewis dot structures actually work for. And for practice, we can draw the Lewis dot structures for the following elements. And here are examples. Phosphorus is group 5, so it has 5 electrons. And again, they go in singly, and then they pair up, and beryllium only has 2. Why draw Lewis dot structures? Lewis structures can show how elements bond, and they can predict their structures. They can also show what type of bond is formed, and that's more for just like the ionic bonds. So ionic compounds and Lewis dot structure. An ionic compound is made up of a metal and a nonmetal, and of course the metals are on our left-hand side of the periodic table and nonmetals are on the right, and this is in general. The metals want to lose electrons and the non-metals want to gain electrons. So what happens is the metal is going to lose electrons to become a positive ion, which is called a cation, and the negative metal gains electrons to become negative, which is called an anion, and then they're attracted to one another, and that attraction is actually the ionic compound. So here's an example. We have potassium that's group 1, so they're showing it's 1 electron in red. And chlorine, which is group 7, so it has 7. So you can see chlorine 7 electrons around, and they did 1 in green just to show that is the one that's going to do the bonding. So that in the end, potassium loses its electron to become +1, and chlorine gains an electron to become -1. So practice for ionic compounds, write the Lewis dot reaction, I guess is what you would call it, for calcium plus chlorine. And here's our answer. Calcium is group 2, so it has 2. Chlorine has 7. So calcium needs to lose 2, and each chlorine needs to gain 1. So you actually need 2 chlorines for every 1 calcium. Lewis dot structures for covalent or molecular compounds. And again, these are generally going to be nonmetals, so on the right of the periodic table. So the octet rule. For most bonding, elements want 8 electrons. There are some exceptions in quite a few of them. Group 1 wants 2 electrons, so that's hydrogen and down. Group 2 wants 4 electrons, that's beryllium down. And group 3 actually only wants 6 electrons, but they can take more. So here's our procedure for the Lewis dot structure. First thing you're going to do is get the total number of valence level electrons, draw a provisional skeletal structure, meaning putting the bonds in, count the electrons that you have left, and distribute them among the rest of the electrons, and check for octets, if the element wants the octet, and then check to make sure that it makes sense. Okay, so we have a practice problem. And here we've got chlorine, so we'll do step 1, which is to count our valence level electrons. It's 7 times 4, so we have 14 electrons. Step 2 is to write our structure. We have the chlorine bonded to the other chlorine, because that's the only thing we have. And then we're going to talk about the bond uses 2 out of the 14 electrons, so there are 12 left to place. So I'm going to put 6 around each chlorine, And then you can see by my circles, they both have 8 and they're happy, so the octet rule is fulfilled. Here's some other practice ones, and we'll pause here to take a minute to do them together. And then here are our answers. And just keeping in mind that beryllium does not follow the octet rule because it's a group 2. It only wants 4 electrons or 2 bonds. Boron also does not follow the octet rule. It wants 6 electrons or 3 bonds. And chlorine does follow the octet rule, and it wants 8. Another example is BH2. Actually, it should be BH2 minus. Sorry about that. I don't know what happened to the minus. And here's our answer.